All right, everybody, I wanted to do a video with a couple more examples, these ones having to do with half-life. So I imported a few things here. So the first is from a couple of videos ago, we worked out this kind of relationship. We talked about what half-life is and what happens in terms of our relative growth rate when we know the half-life, right? So if we know the half-life, and we'll remind ourselves what half-life is in a second, then the population decay model is A of t is equal to a sub 0, the initial amount, e to the power natural log to the power t over h, which of course consolidates into a sub 0 times 1/2 to the power t over h. Okay, so let's look at the problems here. The half-life of strontium-90 is 28 years. Now, the strontium-90, oftentimes when you're talking about radioactive compounds, there's a number after the name to indicate that there's multiple different isotopes of this. So the 90 is just part of the name. It's not actually important to the problem. But the half-life is 28 years. So we're going to highlight that. And then how long will it take a 60 milligram sample to decay to a mass of 28.8 milligrams? So let's just label a few things here. This is our initial amount, right? We're starting with 60 milligrams. And then this is the amount after some time t, except we don't know t, right? So find t. In fact, you can see here in the problem that you are looking for a number of years. If you look at the answer blank, it's a number of years. Okay, so here goes. Now, we know that the half-life is 28 years. So I'm going to go ahead and write that here, that H is 28. So what I really recommend, just like in the previous video, is I really recommend that you actually write out what this means. This means that whatever the initial amount was, 28 years later, you're looking at half of that. So this is kind of the process for finding, I wrote 28T. I should have written 28K. This is the process for finding K. So how to find K. And even though we kind of talked about the general approach to this in a previous video, I highly recommend you go through this a time or two or even more to really get the hang of why K is going to end up being the natural log of 1/2 over h. So just like before, you divide both sides by a sub 0. You'd end up with 1/2 is equal to e to the power 28k. You'd take the log, or in this case, the natural log of both sides. And I'm not going to go through this process again, but by properties of logarithms, the natural log of e to the power 28k is just 28k. So sure enough, k is the natural log of 1/2 over 28, right? So that's what we have in this formula, that the relative growth, the k, is the natural log of 1/2 over the half-life. And again, since this is a decaying situation, the amount of this isotope is declining over time, we're expecting K to be negative, and sure enough, the natural log of 1/2 over 28 is a negative number, which tells us that we're looking at a decay situation. Okay, good. Now, since we know the initial amount and we know how much we are ending up with, let's go ahead and solve this problem. So 28.8 milligrams is how much we ended up with, and that's 60 times e to the power natural log of 1/2 over 28 times t, but you'll remember in our previous video, we actually said, hey, you can write that as base 1/2, and that's a little cleaner. So I'm actually going to go ahead and do that. So it's 60 times 1/2 to the power t over h, which the half-life is 28. So I'm going to solve for t here. This is an exponential equation, so we're going to solve for t. And we do this the way that we do with every exponential equation. We start by dividing both sides by 60. I'm actually not going to do any punching into my calculator yet. We will later, because the sooner I start rounding, the more rounding error I admit. Okay, so I'm going to go ahead and take the log of both sides. And again, I'm not rounding anything yet. I'm just going to write it as the natural log of 28.8 over 60. And here I have the natural log of 1/2 to the power t over 28. And as we've said many times before, properties of logarithms allow the power to pop out. So it becomes t over 28 times the natural log of 1/2. And since we want t by itself, we're going to multiply both sides by 28. And then we're going to divide it by the natural log of 1/2. Okay, so that's the precise answer, but you'll notice in the problem it says round your answer to the nearest whole number. So we're going to punch this into a calculator to get a sense of what this is. But before we do, I just want to say one thing. Look, you started with a 60 milligram sample and you decayed down to 28.8. 28.8 is a little bit more than half gone, right? So a little bit more than half of your initial compound has decayed. So since you know that the half-life is 28 years, we're expecting a number here that's a little bit more than 28 years, since a little bit more than half is gone, but not much. So if I punch this into my calculator right now, and I get like 4, I know that's off because I'm expecting something very close to the half-life. And by that same token, if I punch this into my calculator and I get 4 million, I know that's off because I'm expecting something very close to 28. So do that check-in with yourselves. All right, so here goes. So we have 28.8 over 60. And I'm taking the natural log of that, multiplying it by 28. And dividing it by the natural log of 1/2. So what I'm getting here, and I'm going to write 29.65 here in blue. But of course, in the problem, we're told to round to the nearest whole number. So I'll do that, and I have 30 years. So again, this fits with our kind of reasonable estimate because it's very close to the half-life, but a little bit more. Okay, let's look at this next problem. So in the next problem, we are dealing with a wooden artifact from an ancient tomb, and it contains 70% of the carbon-14 that is present in living trees. How long ago was the artifact made? And then you'll notice it says here, and I'm going to highlight this part, the half-life of carbon-14 is 5,730 years. And then finally it says round to the nearest whole number. Okay, so again, I'm not going to go through the same song and dance as I did in a previous problem, but I encourage you to do that. So this whole piece where you walk through finding the decay constant or the rate of decay when the half-life is known. I'm not going to do that to save time, but I really encourage you to because I think it'll really build up your understanding. Okay, now let's see here. Well, we're not told what the initial amount is. I'm actually going to write that here kind of as a So note, we don't know A0. We don't know A sub 0, but we don't actually need to know it because whatever it was, whatever that amount of carbon-14 present in living trees is, we know that this wooden artifact contains 70% of that. So whatever it is, but we do know that A of t is equal to 70% of A0, or 0.7 A0. So check it out. 0.7 A0 is equal to A0, again, I don't know what it is, and I don't need it, it turns out, times, and then again, I'm going to use this model that we developed a couple of videos ago, times 1/2 to the power T over H, and we know the half-life here, it's 5,730 years. Okay. And now, this is an exponential equation, and we're going to solve for t. And we're going to do it exactly the same way we did it in the previous example. So we'll start by dividing both sides by a sub 0. Oh, so you see now why we didn't really need a sub 0. It just got divided out straight away. Okay. And now we're going to take the natural log of both sides. Like that. And then to get t by itself, we're going to divide both sides by the natural log of 1/2 and multiply both sides by h, which is 5,730. So we have 5,730 times the natural log of 0.7 divided by the natural log of 1/2. So just as we did in the previous problem, we'll punch this in and kind of see what we get. But I want to take a second to kind of check in regarding what we're expecting. So 70% is still there, right? 70% is significantly more than half. So less than half has decayed away. Now, it takes 5,730 years to get down to half of its original amount. So since we are only 30% gone, since 70% is still there, we're expecting a number significantly smaller than 5,730. Maybe 5,000, right? But certainly if I get an answer like 12, that's too little, because a significant amount has decayed away, just not quite half. And by that same token, if I get a number bigger than 5,730, I know that's off too. So keep this in mind as you're punching it into your calculator. All right, so here goes. So we have 5,730 times the natural log of 0.7, and then divided by the natural log of 0.5. So this is approximately 2,948.50. Okay, so it's actually quite a bit less than the half-life. In fact, let me just punch it in one more time to be sure that I'm getting it right, since there was that one typo in a video I made. Okay. Yes, 2,948.5. By the way, always check my calculator work, because once in a while there are little typos and we want to be careful. Since again we're being asked to round to the nearest whole number, I'm going to round this up to 2,949 years. Okay? All right, so that's two problems involving the decay model, and I also think that this is nearly our last video on the whole concept of exponential growth and decay. I have one more little video to show you, but it'll be very short and almost more for your own kind of fun than something I would test you on in class. Have a good day. See you soon. Bye.